Every year, over 150 million carats of diamonds are mined worldwide. But did you know that some mines are so deep that the temperature inside exceeds 110 degrees Fahrenheit, and powerful explosions can cause seismic tremors felt up to 50 miles away? Diamond mining isn't just digging. It's a full-scale scientific operation that starts with satellite analysis and can last for decades. How are these precious stones found? How do drilling rigs reach depths of 10,000 feet? And what happens to diamonds after they're mined? Let's break it down together. Diamonds form deep beneath the Earth's surface and are brought up through volcanic processes that create kimberlite pipes. These pipes, made of ancient igneous rock, are the primary sources of diamonds and can reach depths of over 10,000 feet, with temperatures inside the mines exceeding 110 degrees Fahrenheit. To cool these environments, powerful ventilation systems compress air. In some mines, the air is so pressurized that if a door between compartments is suddenly opened, the wind force can knock a person off their feet. Sounds dangerous, right? Before mining begins, geologists conduct extensive exploration that can last for decades. The process starts with analyzing satellite images and aerial photography. This is followed by field studies, where geologists collect rock samples for chemical analysis. Special attention is given to the presence of indicator minerals like garnets, ilmenite, and pyrope, which suggest the potential presence of diamonds. If the exploration yields positive results, detailed surveying begins. Drilling rigs create boreholes up to 10,000 feet deep, extracting core samples, cylindrical sections of rock. These samples undergo thorough laboratory analysis to assess the diamond content in the rock. Geophysical methods like magnetic surveys, electromagnetic scanning, and gravimetry are used. Open pit mining is employed when the deposit is relatively close to the surface. Underground mining is used if diamond-bearing rocks are located at significant depths. Mine shafts are constructed, allowing workers and equipment to descend. Mining begins with drilling boreholes into the kimberlite rock. For this, massive drilling rigs over 50 feet tall are used. Each borehole can reach lengths of 2,000 feet, and a single mine may have tens of thousands of such holes. After drilling, explosives are placed in the boreholes, and the detonation occurs under strictly controlled conditions. Some diamond mines use such powerful explosives that underground blasts can trigger minor seismic tremors detectable over 50 miles away. First, vertical shafts are dug, reaching depths of over 10,000 feet. The diameter of the main mine shafts often exceeds 20 feet. Additionally, horizontal tunnels are constructed, stretching for several miles. After the explosion, the rock in the mine breaks into pieces of various sizes, from large boulders to fine gravel. Powerful loaders with buckets lift the debris and transport it to central transfer points. Here, massive dump trucks, each capable of carrying over 250 tons of rock, load the extracted material and deliver it to the main tunnels. In some mines, instead of trucks, specialized electric trains running on tracks tens of miles long are used, capable of transporting over 500 tons of kimberlite rock per trip. The main tunnels are equipped with conveyor systems that start at depths of several thousand feet and extend to the surface. The length of these belt conveyors can exceed 15 miles, with belt widths over 6 feet. Some systems have multi-level structures, allowing simultaneous material transport from different parts of the mine. Before being placed on the conveyor, large rock fragments pass through crushing stations, where massive steel rollers over 20 feet long break the debris into fragments no larger than 3 feet in diameter. The crushers operate with compressive forces of tens of thousands of pounds per square inch and can process over 10,000 tons per hour. After initial crushing, the material is loaded onto the main conveyor belts, which transport it to the washing system. In some sections, the conveyors pass through special grottos equipped with giant sieves with holes of various sizes. During transport, smaller rock particles are sifted and directed to separate processing lines, while larger pieces move to the next stage of crushing. The newest mines are equipped with automated control systems that analyze the rock composition in real time and adjust conveyor speed and crushing intensity. As the future diamonds approach the surface, they are fed into special bunkers where the rock accumulates, ready for further processing. The capacity of these bunkers can exceed 100,000 tons, and their structure allows for even material distribution to washing and sorting facilities. In mines located in deep regions, transporting the rock can take several hours, with annual extraction volumes reaching millions of tons. When I was a kid, my family loved going to the beach. It didn't happen often, my dad rarely had time off, but when it did, everyone was thrilled and happy. Diving underwater to find seashells, crabs, or even clams, I never imagined that diamonds could be mined from the sea. Deep-sea diamond mining is one of the most complex and technologically advanced methods in the mining industry. Mines are located where kimberlite pipes or alluvial deposits lie beneath the ocean floor at depths exceeding 500 feet. Geologists begin by conducting surveys using underwater drilling rigs. These rigs are stationed on specialized offshore platforms or vessels equipped with computerized navigation systems for precise positioning over potential deposits. Once diamond-bearing deposits are confirmed, the construction of an underwater mine begins. This is a complex process involving the creation of sealed tunnels or the use of massive drilling capsules operating under high pressure. One method involves using giant seabed drilling complexes, which can exceed 200 feet in length and weigh over 5,000 tons. These complexes are equipped with diamond-tipped drills capable of cutting through even the hardest rock. During drilling, a specialized hydraulic system creates a water flow under pressures exceeding 3,000 pounds per square inch, washing out small rock particles and diamonds into special reservoirs. Another method uses giant underwater vacuum systems that can descend to depths of up to 1,000 feet and suck up hundreds of thousands of cubic feet of rock per hour. The material is then brought aboard a vessel or platform for initial processing. Special underwater crushers can process up to 50 tons of kimberlite rock per hour. Powerful pumping systems are used to transport the rock to the surface, capable of moving up to 1 million gallons of water per day. Streams of enriched rock are directed through pipelines that can stretch for several miles. The material then enters large sorting tanks, where it passes through gravity separators. Heavier diamonds settle at the bottom, while lighter particles are washed away and returned to the sea. Remotely operated underwater vehicles play a crucial role in deep-sea mining, operating at depths of up to 10,000 feet. They are equipped with manipulators that can precisely collect large diamonds directly from the seabed. Their high-resolution cameras allow operators, located hundreds of miles away, to control the process in real time. Deep-sea mining is so complex and costly that only a few countries in the world have the necessary technology. It can cost hundreds of millions of dollars, and the full mining cycle can take over 10 years. Despite the challenges, this method yields millions of carats of diamonds annually, supplying the global market with precious stones hidden in the ocean's depths for billions of years. On the surface, the extracted rock is crushed in processing plants, where massive steel jaws over 20 feet long break the stones into fragments smaller than 2 inches. Each plant can process over 10,000 tons of material per day. After crushing, the rock passes through a series of washing tanks filled with water and chemical reagents. Diamonds, which have high density, settle at the bottom, while lighter minerals are washed away. Once the material is on the surface, specialized X-ray separators are used to identify diamonds based on their ability to fluoresce under ultraviolet light. Magnetic separators work by exploiting differences in the magnetic properties of materials. Diamonds are non-magnetic, while most minerals in kimberlite rock have weak magnetic properties. In these systems, the rock is fed onto rotating drums over 20 feet long, which generate strong magnetic fields exceeding 10,000 Gauss. Magnetic mineral particles stick to the drum's surface and are removed into a separate container, while diamonds and non-magnetic rock residues move forward. X-ray systems are used in the next stage, when the rock is already significantly purified. These systems rely on diamonds' unique ability to fluoresce under X-ray radiation. The stones enter a special tunnel where they are exposed to X-rays with energies of up to 200 kiloelectron volts. The diamonds begin to glow, and highly sensitive optical sensors instantly detect their location. The system then activates a high-speed air jet operating at pressures exceeding 100 pounds per square inch, which literally blows the diamonds out and directs them into a collection container. The cleaned diamonds are sorted by size, quality, and color. The sorting process is fully automated and managed by operators in specialized control centers. Each operator monitors dozens of X-ray systems using high-resolution computer panels. Modern systems use machine learning algorithms that can adjust equipment parameters in real time for maximum efficiency. If malfunctions or deviations occur, operators can manually change settings or redirect material flows for reprocessing. A single system can process up to 20 tons of material per hour, with precision that detects even the tiniest diamonds smaller than 1/10 of an inch. At large diamond mines, dozens of such systems operate simultaneously, extracting hundreds of millions of carats annually. After sorting, the diamonds are sent for cutting, where artisans use lasers and mechanical tools to transform them into precious gemstones. Once cut, they enter the market, sold as part of jewelry or used for industrial purposes. Every year, more than 22,000 short tons of amethyst are mined all over the world. But how do these unique purple crystals end up on display in jewelry stores? Picture enormous geodes, each roughly the size of a person, packed with dazzling crystals that miners extract from remote regions in Brazil, Uruguay, and Africa. Some of these geodes are so rare that they are transported by helicopters. However, did you know that only about 10% of all discovered amethysts are of jewelry quality? Let us dive into a world where nature creates masterpieces and humankind unveils them for everyone to see. Brazil is one of the largest suppliers of amethyst on the planet. The main deposits are located in the states of Rio Grande do Sul and Minas Gerais. In Brazil, amethyst geodes are often found, which are hollow stone formations lined with crystals on the inside. Some geodes can reach over 9 feet in height. Uruguay is famous for its amethyst that has a rich, dark purple hue. This stone is usually of higher quality than the Brazilian variety. Geodes from Uruguay are considered extremely valuable because of their depth of color. The African continent, particularly Zambia, is also an important source of amethyst. Zambian amethysts feature a unique purple color with a bluish tint. They are mined in considerable volume, but the deposits are located in hard-to-reach regions, making transportation more complicated. Amethyst deposits in the United States are not as large-scale as in Brazil or Uruguay, but they have their own special history and appeal. The amethyst found in the United States is prized for its vibrant coloring, historical significance, and local popularity. So, let us take a closer look at the main locations and their distinctive features. Four Peaks is the most renowned and likely the largest amethyst deposit in the United States, situated in Arizona, at an elevation of about 7,545 feet above sea level. The amethyst from Four Peaks is noted for its deep purple color with a subtle reddish glow. Many believe these stones can compete in quality with even the most valuable specimens from Uruguay. The deposit is located in an extremely challenging spot. There are no roads, so miners and equipment are transported by helicopters or on mules. This is one reason why stones from this deposit are so expensive. The mining process is physically demanding and costly. Most of these mines are small, and much of the work is done manually to avoid damaging the crystals. A modest region in the northern part of Georgia is home to lighter, pastel-toned amethysts. Although the deposits are not as extensive as those in Arizona, the stones exhibit a unique clarity and a pleasant purple hue suitable for more affordable jewelry. Local specimens are often mined in small private shafts or even during special tours that allow tourists to try their hand at being treasure hunters. This aspect adds a certain charm to Georgia amethysts, as they become both a souvenir and a cherished memory. The Creede area in Colorado was once more famous for its silver mines. However, there are certain spots where amethyst deposits can be found as well. These stones tend to be lighter in color and less intense in saturation, yet they possess interesting inclusions that give them a unique character. Amethysts from Creede are frequently used to make cabochons, which are smooth, unfacetted stones suited for decorative ornaments. Amethyst usually forms in volcanic rocks, where high temperature and pressure conditions cause quartz to absorb iron impurities, then cool over thousands of years. The outcome is a deep purple crystal that makes you pause and exclaim, Wow! For example, in Brazil, miners uncover enormous geodes lined with crystals. Sometimes these geodes are so large that they appear at exhibitions, where people take photos beside them, as if they were standing next to a work of art. Now imagine this scene: a team of miners wearing hard hats, equipped with headlamps and pickaxes, searching for just the right pockets of stone where these priceless cocoons lie hidden. Believe me, it is no simple task. Today, miners do not rely solely on luck in their pursuit of amethyst. Their primary allies these days are science and technology. The process starts with detailed geological mapping. Geologists investigate regions that are well known for containing abundant quartz, the primary mineral from which amethyst arises. For instance, in Brazil, the world's largest amethyst producer, researchers target geological formations ranging in age from 50 million years to 200 million years. One of the most advanced tools is high-resolution satellite imagery. Through spectral analysis of the colors on the Earth's surface, specialists can pinpoint hues that hint at the presence of specific minerals, including quartz. Moreover, seismic sensors contribute to the creation of three-dimensional models of the underground layers of soil. These devices detect even minute reflected waves that tell the story of the materials hidden below the surface. Yet, as strange as it may sound, intuition and hands-on experience still play a huge role. For instance, miners in Rio Grande do Sul in Brazil claim that deep reddish-brown soil nearly always indicates proximity to amethyst. Such observations help them concentrate their efforts exactly where the odds of discovering stones are the greatest. Statistics show that only about 5 to 10% of all areas that look promising based on maps or satellite data actually harbor commercially valuable deposits. In Brazil, which accounts for over 40% of the global amethyst market, dozens of new zones are surveyed every year, but only a handful proceed to the extraction phase. The average depth of an amethyst mining site seldom exceeds a few dozen feet, but these locations demand enormous amounts of preliminary work. According to the United States Bureau of Mines, launching a single mine may require as long as 3 years and cost anywhere from $50,000 to $100,000 before unearthing even a small pocket of amethyst. This illustrates how labor-intensive and expensive the quest can be, even for gems as popular as amethyst. Ultimately, technology, expertise, and a hint of intuition collaborate to uncover those mysterious purple treasures that we admire in jewelry. Although the probability of finding the ideal crystal is slim and the miner's work is strenuous, the reward is unquestionably worthwhile. The amethyst extracted from a mine looks nothing like what you see in a display case. It is often covered in rocky residue, irregular in shape, sometimes almost opaque. Once it is mined, the stone goes to a factory, where a kind of magical transformation unfolds. First, the crystals are cleaned, occasionally by hand, and occasionally in massive tumblers that literally scrub away the dirt. Then each stone is sorted by quality. Here is the interesting part. Only about 10% of all the amethysts unearthed are of jewelry-grade quality. The rest are used for more budget-friendly accessories or even ornamental items. The next step is cutting. This is a true art that merges careful science with the delicate touch of a skilled artisan. Picture a person peering through a loupe, meticulously turning the stone to find the ideal angle. The most fascinating aspect? One slip of the hand can cause the crystal to crack. Let us suppose the stone is finished. The next issue is transportation. This task is not as straightforward as one might initially assume. Certain amethysts travel in specialized boxes, padded with foam inserts to protect them from the faintest jostles. In the case of geodes, they are often packed in wooden crates lined with soft materials. Uruguay has a distinctive export program for its amethysts. Stones are sold directly at auctions, drawing buyers from all over the globe. In Brazil, on the other hand, most of the output goes straight to large enterprises that handle both cutting and further distribution. The price of amethyst is determined by factors like color, clarity, and size. The most expensive pieces boast a vivid purple tone with a slight reddish shimmer, often called deep royal. Such stones are frequently utilized in luxurious jewelry, which can appear at international auctions. Here is something surprising. Even though technology has improved remarkably, a great deal in this field still hinges on human effort and observation. It is a tradition passed down through many generations. Even the extraction itself relies more on manual labor than on large machinery. Initially, after identifying a promising zone, preliminary work begins. If the amethyst is near the surface, excavators remove the topsoil, creating large open pits. In places like Minas Gerais and Bahia in Brazil, these open pits can span several dozen feet across. However, if the amethyst is buried deep, the operation goes underground. Mines that yield this crystal can extend about 320 feet into the earth, forming a vast maze of tunnels branching out in all directions. Breaking through the tough layers of rock is the first step to reaching amethyst. This may involve using explosives or drill rigs, but it is not as dramatic as one might imagine. It must be done very carefully to avoid shattering the precious crystals. The people responsible for this work are genuine experts. They even live by an informal motto: "It is better to go around than to destroy." A carelessly managed blast can reduce a stone to fragments. Once the deposit is exposed, miners proceed by hand or with small tools to gently dislodge the crystals. Envision the scene: darkness, illuminated only by the glow of headlamps, and silence broken by the occasional strike of a pickaxe or the hum of a handheld saw. Everything relies on the miner's dexterity. Even the most subtle motion can determine whether a crystal remains intact or breaks. Some refer to this phase as jewelry-level work. The amethysts that are found are typically surrounded by quartz rock and clay, so they are cleaned right there in the mine. This is painstaking work, removing layer after layer and taking care not to harm the delicate crystal structure. It is reminiscent of restoring an antique vase. The most valuable crystals are separated by hand, with every movement carefully planned. Interestingly, the ambience in these mines can be quite a spectacle. For example, in the famous Las Vegas mine in Uruguay, amethysts shimmer in the darkness under the beam of a lamp, creating the sense of stepping into a magical subterranean realm, radiating shades of purple and blue. In some locations, such as the Amethyst Park in Brazil, the mines are open to visitors, and people can witness firsthand how skilled workers gently extract the crystals from the walls. Those workers are the real heroes. They toil in challenging conditions. Imagine this. One ship contains up to 20,000 tons of steel. That's the weight of 3 Eiffel Towers. But what happens when these ocean giants retire? Every year, more than 1,000 vessels are sent for recycling, and their materials find new life in bridges, cars, and even other ships. This isn't just dismantling, it's giving metal a second life. Stick around to see how this global process is changing the world. The beginning of the end, or why are ships dismantled? Ocean vessels have an expiration date. On average, that's about 25 to 30 years. After this, maintaining them becomes uneconomical and their structures unsafe. This is where a process, often called shipbreaking, begins. Remember those movie scenes where ships are shattered by waves? Well, no waves are needed here. Just welding tools, massive cranes, and teams of workers who know how to handle these metal giants. First, everything is stripped from the ship. Furniture, electronics, pipes, and cables. Even doors and windows. All of this can be recycled or reused. This process is usually carried out by hand, though sometimes specialized equipment is used. Workers physically dismantle the interior of the ship, unscrewing bolts, cutting metal pipes, removing doors, windows, and panels. It's meticulous, labor-intensive work, requiring attention to detail and strict safety protocols. Imagine this. Cables need to be carefully extracted so they can be sold as copper scrap, and chemicals, such as leftover paint or lubricants, must be safely removed. Even furniture is taken apart to salvage wood or metal components. Of course, on large shipyards, workers are aided by mechanical tools, cranes, gas cutters, and sometimes robots to handle hazardous materials. But the bulk of the work is manual labor. That's why, in countries like Bangladesh or India, where labor is cheaper, shipbreaking is so popular. This stage is crucial because properly preparing a ship for dismantling prevents leaks of chemicals and toxic materials that could harm the ecosystem. Oil, fuel, and chemicals all are drained from the ship to avoid environmental contamination. Once the ship's hull is stripped of everything unnecessary, the gas cutters take center stage. Massive, rusty steel walls, the very structures that once kept the ship afloat, are gradually turned into individual pieces of metal. Workers, dressed in protective suits, stand directly on the hull. Their cutters create bright orange sparks, flying in all directions, producing a kind of steel fireworks. It's both mesmerizing and slightly intimidating. The cutter heats the metal to such a high temperature that it literally melts. But it only looks easy. Ships aren't just piles of steel. They're labyrinths of multiple layers of metal. Sometimes workers have to cut through several layers to reach the right spot. Cutting begins with the upper decks. Large sections are first carved out, like chunks of sidewalls, decks, or even parts of the hull, which are then lifted by cranes and loaded onto platforms. From there, they're sent to factories, where the pieces are recycled into new steel or aluminum. But it's not just about cutting, it's about doing it safely. That's why the hull was cleared earlier of any leftover fuel, lubricants, or other hazardous materials. Without this step, gas cutters could trigger explosions. So, this process is not just labor, it's an art that requires strict adherence to safety rules. And of course, all this happens under the blazing sun or in humid coastal climates. Workers quickly adapt to the heat, and even sparks flying at their feet become a routine sight. In the end, they witness the transformation of a massive, once indomitable ship into mere pieces of metal. It's almost like watching a rebirth. Imagine this. Those massive steel blocks that once kept a ship afloat become the foundation for new bridges, buildings, or even other ships. About 90% of a ship's materials can be recycled, and the largest share is steel. A single large ship can yield up to 20,000 tons of this metal. That's the equivalent of 3 Eiffel Towers in weight. Once the ship's hull is cut into pieces, the next thrilling phase begins, transporting the steel to factories. And trust me, it's not as simple as throwing it on a truck and driving off. These metal pieces are usually so large and heavy that they can't be moved by conventional means. Massive cranes, the kind that look like they could lift a ship themselves, dominate the scene. Their long metal arms with hooks or magnetic platforms carefully grab steel sections and lift them off the ground. It's almost like watching giant toys in action, but everything is done with surgical precision, because one mistake could be costly. After that, the steel is loaded onto huge platforms or special trucks. Regular trailers won't cut it here. You need vehicles with reinforced frames capable of bearing tons of weight. Imagine this. One section can weigh several dozen tons. Sometimes, rail cars or barges are used for transport if the factory is near a port or river. This helps cut down on delivery costs because moving steel is no cheap task. The journey to the factory can be long. For example, if a ship is dismantled somewhere in South Asia, its materials might be sent as far as Europe or America. In such cases, the metal is loaded onto ships again, but this time on cargo vessels. Full circle, right? A ship becomes raw material transported by another ship. Once at the factory, the metal is carefully weighed. Every detail matters, from the total weight to the precise composition of the metal, as different alloys require different processing. Only then does the steel head to the melting stage, where its new life begins. This steel will become new construction materials. Ships continue their legacy, not in the ocean, but as skyscrapers or train tracks. But it's not just steel that's valuable. Ship components also contain aluminum, used in car and airplane manufacturing. Wooden elements, rare in modern ships but present in older ones, are restored and sold for decor. Fabric from old seats is sometimes repurposed into bags or even rugs. Isn't that cool? You buy something stylish and later find out, oh, this was on a liner that sailed the Caribbean. But it's not all smooth sailing. Ship recycling can pose environmental risks if done irresponsibly. Ever heard of Alang? It's the world's largest ship recycling yard, located in India. There, ships are literally beached and dismantled by hand. This method is cheap, but dangerous. Oil and chemicals can leak into the water, and workers often lack proper protective gear. Recently, however, the world has started paying attention to this issue. More and more ships are being recycled at specialized yards that follow strict environmental standards. For instance, in Europe, regulations require the safe storage and disposal of hazardous materials. The largest ship ever dismantled was a container vessel measuring 1,312 feet in length. Imagine taking apart such a giant. This container ship, Ever Given, became famous in 2021 after blocking the Suez Canal, though its end wasn't due to that incident. When ships of this scale are retired, they're usually sent to one of the world's biggest shipbreaking capitals. Dismantling such a vessel likely took no less than a year, because a mountain of steel, cables, equipment, and other materials is a serious challenge, even for experienced teams. Every piece must not only be cut, but also carefully moved, sorted, and shipped for recycling. At the steel plant I visited, everything starts with thoroughly inspecting the metal pieces. They're cleaned of any paint, rust, lubricants, or other impurities that could affect the quality of the steel. Watch as dozens of hands and machines work to prepare this metal for its next journey. Next, the pieces are shredded, cut into smaller parts that are easier to load into the smelting furnace. The process of cutting metal at steel plants is a spectacle in itself, like something out of a sci-fi movie. Huge workshops filled with sparks, heat, and the hum of machinery. These aren't ordinary scissors. They're powerful hydraulic presses, cutting machines, and even lasers. Each tool plays its part depending on the size and type of metal. First up are hydraulic shears. These massive machines can slice through thick steel like paper. They operate under immense pressure, thousands of tons of force that literally crush and cut the metal. Their crunch echoes throughout the workshop. For finer work, gas or plasma cutters are used. A gas cutter operates by burning fuel. Oxygen and acetylene heat the metal until it melts, and then a stream of gas cuts through it. Plasma cutters are even cooler. They create an electric arc that melts the metal, leaving a clean, precise edge. Then there are laser machines. They work with incredible precision, carving out the tiniest details. The laser beam seems to dance across the metal's surface, leaving behind a smooth, polished cut. This is the technology of the future, already in action at many factories. But this isn't just random cutting. Every step is carefully planned. Metal is sorted by thickness and type to avoid damaging equipment. Larger pieces go through specialized conveyors to the next stage, while smaller ones are sent straight to melting. For melting steel, arc furnaces are used. These massive monsters run on electricity, generating temperatures close to 3,000 degrees Fahrenheit. The metal simply melts, transforming into liquid steel. But that's not all. Special substances, known as ferroalloys, are added to the molten mass to enhance the steel's properties. Need strength? Add vanadium or chromium. Want it lightweight? Add aluminum. It's like cooking, but for engineers. Next, the steel is poured into molds, depending on what it's destined to become. These could be sheets, beams, rebar, or even wire. The castings are cooled, cut, polished, and then shipped off for new projects. Building skyscrapers, bridges, or even new ships, all of this can start with the recycled hull of an old vessel. And isn't it amazing? A ship that once carried thousands of tons of cargo across oceans can become part of a car or the frame for a modern stadium. This second life of steel feels almost magical, doesn't it? Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw-dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection. a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund, often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 1/10 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/1600 to 0.4 of an inch, are suitable for sturdier products like structural elements or, in some cases, new aluminum cans, when further processing requires that specific diameter. Thick wire rods, over 0.4 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 0.04 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end-to-end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. Every year, the world produces over 420,000 tons of snails. That's more than the weight of 300,000 cars. Imagine these slow creatures being transformed into delicacies worth up to €50 per kilogram, or their slime being used in cosmetics priced at up to €300 a jar. Snail farming isn't just a business, it's a billion-dollar industry. Want to know all the secrets? Stick around till the end. Picture vast fields where thousands of tiny snails crawl slowly among the greenery. These are snail farms, and they're more than just a thing. They're a serious business. Europe leads the world in snail farming, with most farms located in France, Italy, Spain, and Poland. The main species grown here are the Helix aspersa, or small gray snail, and Helix pomatia, known as the Burgundy snail. The idea of farming snails has ancient roots, dating back to ancient Rome. Think about it. The Romans were both gourmets and innovators. They were the first to cultivate snails on a large scale for food. How did it work? Romans built special snail gardens where they kept snails, feeding them herbs, fruits, and even wine. Yes, you read that right. They literally soaked snails in wine to make them more tender and flavorful. The famous Roman naturalist Pliny the Elder, who who lived in the 1st century AD, wrote about snails being a delicacy at noble banquets. He even mentioned a Roman gourmet, Quintus Fulvius Lupinus, who established the first known snail farm in the 1st century BC. After the fall of the Roman Empire, snail farming was somewhat forgotten. But during medieval times, monks revived it. For them, snails were a convenient food option during Lent, as they weren't officially considered meat. Clever monks, huh? By the 19th century, snail farms gained popularity in France and Italy, where modern farming methods were developed. The French were the first to turn snails into a gastronomic brand now known as Escargot. In the 20th century, snail consumption increased so much that industrial-scale farms became necessary. Today, we have entire industries, from food to cosmetics, all thanks to this ancient Roman idea. Isn't that fascinating? Every year, over 420,000 tons of snails are farmed globally, with Europe dominating the market. France, for instance, consumes about 30,000 tons of snails annually, half of which are imported. Imagine the scale. Let's start with the snail nursery. Farms begin by collecting snail eggs, those tiny white pearl-like balls. The eggs are carefully selected because the farm's success depends on their quality. To encourage breeding, farms create specific conditions. The air temperature must be around 70 degrees Fahrenheit, with nearly 100% humidity. It's like a paradise for snails. Farmers even use special systems to keep the air moist, ensuring the snail's comfort. The eggs are then moved to incubators, where tiny snails hatch a few weeks later, barely recognizable as the future delicacies. Surprising, isn't it? My friend once had pet snails, and they bred like crazy in any conditions. But here, with all this care, there are no guarantees. Perfection is truly the enemy of good enough. Let's take a closer look at how snails grow. Once they hatch, the snails are moved to open enclosures, special fenced areas on the farm where they can crawl freely. They're fed a mix of grains and vegetables like cabbage, carrots, or even lettuce. Snail care is a science. Farmers regularly check their health, provide plenty of water, and even protect them from natural predators like birds or insects. Fun fact, a snail can drink more water than its body weight. In some countries, snail farms play relaxing music to reduce stress. Snails can take up to 6 months to grow large enough for harvest. Their size and weight depend on the species and farming conditions. Harvesting snails is an art. When snails reach the right size, they are collected, often by hand. Each snail is carefully inspected to ensure it's healthy and high quality. In snail farming, healthy and high quality involves several key factors: physical condition, suitability for consumption, or cosmetic use. A healthy snail actively moves, stretches its body, and responds quickly to stimuli like touch. Sluggish or closed snails might be stressed or sick. Their shells must be intact, free of cracks, spots, or chips, a sign of sufficient calcium in their diet. Healthy snails should also show no signs of parasites, fungal infections, or diseases that could affect their viability. On average, a snail weighs about 1 pound, though the ideal weight varies by species. This is the optimal size for culinary use. Before processing, snails are kept without food for 3 to 5 days to clear their digestive systems, ensuring the product is safe. A snail's diet impacts the quality of its meat, so their meals consist of greens, fruits, and special mixes. High-quality snails have tender, slightly sweet meat. They must be raised without harmful pesticides or fertilizers, as they are highly sensitive to contamination. For cosmetic purposes, snails need to produce a sufficient amount of slime, known as mucin. But more on that later. This requires proper nutrition and farming conditions. Healthy snail slime is transparent, impurity-free, and rich in beneficial components like allantoin, elastin, collagen, and vitamins. Quality snails live for 3 to 5 years, which is crucial for sustainable production. However, on farms, they're usually kept for about 14 months. Modern snail farming emphasizes eco-friendly practices, no soil or water contamination, and an organic approach to feeding. A healthy, high-quality snail grows in ideal conditions, eats a balanced diet, and shows no signs of stress or illness. It's perfect for gourmet dishes or premium cosmetics. Collected snails are washed and sent for further processing. If the farm caters to the restaurant market, the snails are immediately placed in special refrigerators, where they enter a state of dormancy, a natural process allowing them to sleep. Globally, over 420,000 tons of snails are farmed each year, with France, Italy, Spain, and Greece being major producers. Snails move at less than half a pound per second, so to cross a football field, they'd need about 5 hours. But they can endure a 2-hour walk in the rain without a break, the equivalent of a marathon for us. An average farm raises anywhere from 100,000 to 1 million snails. Now, the exciting part. How do these slow creatures become delicacies? First, they're prepped for consumption, washed, cleaned, and boiled. Then, they're marinated, baked, or stuffed with delicious sauces. Did you know French restaurants love serving snails in their shells with a garlic butter sauce? It's their signature move. If food is clear, how did snails end up in cosmetics? It's all about the slime. It contains beneficial substances like allantoin, collagen, and glycolic acid that work wonders on the skin. In ancient Rome, slaves rubbed snail slime on their mistress's skin, believing it healed wounds and rejuvenated. In the 1980s, Chilean farmers raising snails for export noticed their hands became unusually soft, free of cuts or scars. This sparked the idea of using mucin in cosmetics. On specialized farms, snails are kept in comfortable conditions where they produce slime. This slime is harvested without harming the animals and used in creams, masks, and serums. They say this ingredient works miracles, rejuvenating skin and addressing imperfections. The snail slime cosmetics industry is worth $760 million and grows 10% annually. The biggest buyer, South Korea. The slime collection process may seem odd, but it's designed to be cruelty-free. There are two methods: manual stimulation and automated systems. In manual stimulation, farmers gently massage the snail's body or spray it with clean water and sea salt. The snail secretes slime as a natural defense mechanism. The collected slime is washed and sent for filtration. For automated systems, large farms use special devices. Snails are placed in containers where they are gently stimulated with water or air streams. The slime flows into a reservoir for collection. Afterward, the snails are washed and returned to their enclosures. They can produce slime again after a few days, ensuring the process doesn't harm them. The collected slime is purified, leaving only the valuable components. The resulting mucin is rich in collagen, elastin, glycoproteins, and other active ingredients. After processing, the slime becomes a raw material for cosmetics or pharmaceuticals. Snail slime is then used in high-end creams and serums that repair skin and treat acne. To produce 33 ounces of quality mucin, about 50,000 snails are needed. The snail market isn't just about food or cosmetics. In the European Union alone, it's a multi-billion euro business. 1 kilogram of snails can cost between 20 and 50 euros, depending on their origin and processing. Cosmetic products made from snail slime sell for 30 to 300 euros per jar.